Okay, in this video, we're going to pick up with an application. And I want to do these applications on paper here. So let's shift over to the doc cam. I've simplified it for just the first question. Then we'll go to the second one in a minute. But it says the average preschool teacher in California earns $36,000 per year with a standard deviation of 7,500. A new insurance program is made available for those teachers that are in the bottom 20% of the wage scale. Assuming earnings are normally distributed, what is the salary the insurance program directors will use as the cutoff? In approaching these problems, the first thing I like to do is draw the normal distribution. Okay, this way we can visually see what's going on. Okay, and we can split it. Remember, it's symmetrical, and we know that the average is 36,000. So I'm going to put that right here, 36K. Okay. And it says the standard deviation is 7,500. I'll just write that over here. Okay. We want to find out what the salary is for the cutoff of the bottom 20%. So we're going to identify the bottom 20% here, 0.20, and we want to know this cutoff. That's going to be an X value. Okay, we don't have that yet. We need to find it. Okay. To do this, we're going to convert our scale into Z. Right here we have our X values. Right, that's actual values. But let's go to the Z scale, and we know that the mean is 0 for Z. And we want to find the Z that corresponds to this particular point. Well, we can use our tables because remember, the tables will tell us the Z score that corresponds to this particular probability. Now, the way our Z scores are set up in the table, they're all positives. Therefore, we need to think in terms of not 0.2 as the probability, but a negative Z, which means 0.8 as the probability, right? Remember, when you're dealing with negative Z scores, which we know we're going to get, right, because we're below 0, below the mean, when you're dealing with negative Z scores, you always start in your table with the right tail to the left. So if this is 80%, this is 20%. Okay, so let's go to our Z table. Okay. And we're going to find 0.8. And so let's do that. Just scroll around and look for the closest we can get to 0.8, which it looks like is right here, 0.7995, and that corresponds to a Z value of 0.84. That may look familiar because we saw that in the last video for a different problem. But so we have 0.84 and it's negative, .84. So now we have two scales, right? We have the Z scale, which tells us that negative 0.84 Z corresponds to 20% in the lower tail. And we have the X scale, which tells us that this value here, whatever it is, will correspond to 20% in the lower tail. Now we just got to find that. Okay? Recall the formula that we used previously. It says that an X value will be equal to the mean of the data plus the Z value multiplied by the standard deviation. Well, now we have all the information because we know the mean, that's 36,000. Okay, we also know the Z, that's negative 0.84. And we also know the standard deviation, which is 7,500. If you plug these numbers in, you will get 29,700. Okay, and you can double check that with your own calculations, but that means we now have X. So we know that 29,700 corresponds to this, which means that preschool teachers in California would have to make less than $29,700 to qualify for the new insurance program. Okay, you can also use Excel to solve these kinds of problems. I'll pull this over here. For this one, we would use the norm dot inverse. Okay, and if you pull this up, what it's going to do is ask you for the probability, and we know that we want the bottom 20%, so we're going to put 0.20. Okay? It's going to ask you for the mean, which we know to be 36,000, and it's going to ask you for the standard deviation, which we know to be 7,500. Now, given that, you notice it tells you the x value would be 29,687, which is pretty close to what we got. All right, let's move on to the next question. It says, in the construction of all new buildings in San Francisco, the height of an entryway must be tall enough so that 99% of the population can pass through without ducking. If the distribution of height is normal, with a mean of 69.2 inches and the standard deviation is 3.8 inches, find the door height that is required. We're going to follow the same process. Very similar question. Draw our normal distribution here. Identify the mean, and we know that the mean is 69.2 inches. Okay, it's going to represent our x values here. And we want to find a value for x that corresponds to 99% of the population being able to pass through. Well, clearly, shorter heights for the door would be here. Right? So the shorter the door height, the less people would be able to pass through. So as we move this way and move towards higher door heights, we start to accommodate a larger fraction of the population, which tells us that we need to have an upper tail here of 1%, 0.01, meaning that 99% would be here in the lower tail. Okay? But we don't know what that value is. We got to find that. And we're going to do that by standardizing. So we use the z-scale. We want to find the z that corresponds to 1% in the upper tail. Let's go to our tables. Well, if we're looking for 1% in the upper tail, we're actually looking in the table for 99%. Right? So we want to go to 0.99, as close as we can get, and this is it right here, 0.9901. So the z value is going to be 2.33. So 2.33z corresponds to 99% here and 1% here. We also know z standardizes to 0 at the mean. Okay. Once we have that, we can solve for x, right? Because remember our formula? X is equal to the mean plus the z-score times the standard deviation. Well, now we have all three. We have the mean, which is 69.2. We have the z, which is positive 2.33. And we have the standard deviation, which it tells us is 3.8. Now, if you do this correctly, you should get about 78.1. And what that means is 78.1 is that the door height should be constructed to a 78.1 inch height. That ensures that 99% of people would be able to get through, leaving only 1% that would have to duck. Okay, now you can use Excel just like we did in the previous example. We would use the formula norm dot inverse. Okay, and we would select and put in our data. So the probability we just established is going to be 0.99. The mean is 69.2. And the standard deviation is 3.8. Okay? And if you do that correctly, you get 78.04, which is close enough to what we had here, right? 78.1 inches. All right, so two routes to the same end. Let's move on. We've covered extensively the normal distribution, which is one type of continuous probability distribution. It just happens to be the most common in the areas that we would be studying as economists or social scientists. There are two others that do pop up now and again, though, the uniform and the exponential. And all of them are accomplishing the same thing. They're analyzing the probability of a random variable, assuming a value in an interval rather than a specific point. Again, to distinguish from discrete probability distributions like the binomial, Poisson, or the hypergeometric. those analyze probabilities at specific points, whereas these continuous distributions analyze intervals. Example, approximately 16% of Americans are between the ages of 15 and 65. We're not looking at the probability of an American being 15 or 65. We're looking at the probability of Americans being in this range. Okay? In every instance, the total area under the curve equals 1. With the uniform, you'll notice that it takes on this shape, just meaning that any value that we select, the probability is the same. So the probability of getting x1 is the same as the probability of getting x2. Maybe this is 25%, let's say. So the probability of getting this value would be 25%. The probability of getting this value would be 25%. With the normal distribution, probabilities vary across your x values. So x1 clearly has a higher probability of occurring than x2. And then for exponential, the probabilities also vary, but there's a pattern. Probabilities are highest for the lower x values and drop off as we move to higher x values. Let's first look at the uniform in more detail, then we'll shift to the exponential. The uniform probability distribution takes on this shape, which just means that there is a constant probability for any of the x outcomes. Now here we've got flight time in minutes. So the lowest flight time possible is 120, the highest is 140. So the probability of getting any particular value in this interval is going to be 1 over 20, because there's 140 minus 120. There are 20 flight times there. And since it's constant, 1 over 20, which, by the way, is 5%. You can see that in this formula here. To calculate the probability, we simply take 1 and divide it by the high value, b, minus the low value, a, for all values between a and b. Now, any other value, anything below 120 or above 140, the probability would be 0. We've acknowledged with this illustration that this is the range. Okay. But let's do the calculation here. So, for example, the probability of getting an x value, let's say, of 125 minutes, well, that would be equal to 1 divided by b minus a. We got 140 minus 120. Okay. And the result is 1 over 20, which is equal to 5%. So the probability of getting this value is 5%. Okay. Of course, what if you want to find the probability of a particular interval? Let's say we want to know the probability of getting a value between 125 and 130. Well, because we know the probability of every point is 5%, we just multiply it by the interval. The interval here is 5, so the probability is 25% that we get a value between here and here. Right? What's the probability of getting a value between 130 and 140? Well, the probability of each individual outcome is 5%. Okay, so 5 times the interval is 10, it's 50%. So this from here to here would be 50%. If you look at the whole interval, it would be 120 to 140, that's 20 points times 5% is 100. So the probability of getting a value between 120 and 140 is 100%, that kind of thing. Okay. Now, the expected value is going to be equal to the average of the high and the high and the low. So we simply add them together. And we take the low, 120, plus the high, 140, and then we divide that by 2. And if you do that correctly, the expected value is going to equal 130, right? 120 plus 140 is 260, divided by 2 is 130. Okay? And then finally, the variance. Well, for the variance, you're just going to take the higher value, b, which is 140, subtract the lower value, 120, you're going to square that, and you're going to divide it by 12. Okay? And if you do that correctly, you should get a variance equal to 33.33. Okay, that's how we calculate the probability, expected value, and variance for a uniform distribution.